Okay, so hello and welcome back. So in this video we want to talk about a little bit about proofs in mathematics, and basically the way and the reason why we are doing that is that basically from now on we will have to prove things, and so you need to get a little bit to get more familiar with how to prove things in mathematics, how the structure of the whole proving things in mathematics is. So for that reason we just need to basically get more familiar with the whole structure of logic and proving in mathematics. So so at the heart of this system, and this system is actually nothing but simple logic, but as it turns out, we as human beings are not very logical beings. We live our lives a little bit differently. There are other forces working in us, forces other than logic. And so basically when you want to do proofs in mathematics, you have to learn this system. Otherwise this system I suppose is actually the right way to use logic. But then in our day-to-day lives there are other factors as well that govern our lives. So basically our lives as people are a little bit different, meaning that it's not 100% logical. So now at the heart of this system of logic lies basically proofs or evidence, basically. Meaning that, for example, if somebody, for example, let's say that you have a piece of land in a village and somebody, for example, puts a fence around a piece of your land. In order to take your land back from that person, if that person refuses to give your land back, and if, for example, the village elders are not able to help you out with the situation, then you'll have to produce some sort of proof as to basically, you'll have to basically produce some sort of proof and show the other person, for example, or show a court of law that, for example, this piece of land from this spot all the way up to this spot belongs to me, and then that way you could, for example, take your land back, meaning that here you have to produce a proof or evidence that this land belongs to you, and then you have to prove it. Okay? Or, for example, suppose that you get a phone bill for the month of August, for example, and you pay the phone bill. So in the month of September you get another phone bill, but then you notice that the amount for the month of August has again been charged to your account. So in order to have that amount for the month of August, to have that basically reduced from your bill, to have that reduced from your bill, you will have to basically produce an evidence or a proof that basically you have paid your phone bill, for example, the previous month, and that proof usually is the receipt that you got the previous month, and that way you can solve the problem. Or now in mathematics, basically, now in our day-to-day lives, we usually accept things without any proofs. For example, I don't know, there is, I could give you many examples. For example, usually people are I mean, things are just the way that they are. You don't usually ask for proof. And if you ask for proof, you would be thought of as a weird person. But and we also basically accept many statements without bothering for any proofs. Basically, you accept many statements from other people accept many statements from you, and you don't want the other person to prove what they're saying, and the other person in the same way don't want you to prove what you're saying. And if you pay attention to basically a typical day in your day-to-day life, you'll see that you are making a lot of logical mistakes. Other people in turn are also making a lot of logical mistakes, and nobody is really bothering, because nobody is really nobody catches the mistakes really. But the logical mistakes are always there. Now, I don't want to get into that sort of thing, but basically in mathematics, we only accept a statement as true or false if it has been proved to be so, according to the logic of mathematics. So this is important. So in mathematics, we only accept a statement as basically true or false if it has been proved to be so. Otherwise, and that has to be that must have been proved according to the logic of mathematics. Okay, which is basically what we are doing here. And as I mentioned, basically, it is actually believed that it is believed that the first person that ever actually produced the first proof ever in the history of mathematics, something like that, was the Greek philosopher and mathematician Thales. And that's basically the whole story here. Now, there is basically a concept which is basically mathematically acceptable statements. So mathematically acceptable statements so what that is, basically, first of all, you need to know what a statement is, and then we'll get to the rest of the story here. So first of all, in mathematics, basically we could, in our day-to-day lives, we can have different forms of sentences. So a sentence can be a question. It can be a question. It can be an order. It can be an exclamatory remark. Okay, so a sentence basically could be a question. For example, you could ask, for example, what time is it? What time is it? So this is a question. Or basically as an order, for example, you could say go to school. Okay, or as an exclamatory remark, you could say, for example, what a beautiful house. What a beautiful house. Okay, So these are the kind of sentences that is, one of them is a question, the other one is an order, the other one is an exclamatory remark, and none of them is actually a statement. So a statement is basically a sentence which is not a question, which is not an order, which is not an exclamatory remark. This is a hard word to pronounce. Which is not an exclamatory remark. So that if these three are not the case, then you will have then your sentence is a statement. Okay, so then you have a statement. So and in mathematics, basically a statement can have basically three different conditions, meaning that it can be it can be always true, it can be always true, or it can be always false, it can be always false, or it can be an ambiguous statement. An ambiguous statement. Okay, so we will basically talk about the part where it is always true or always false. But about a statement being ambiguous, basically what that is excuse me. So about this statement being ambiguous, so usually in two ways a statement can be ambiguous. So a statement can be ambiguous when not enough of a context has been given to you. For example, let's say that, for example, you say tomorrow is Thursday. Okay? So this sentence is an ambiguous sentence. I'm sorry, this statement is an ambiguous statement because there is no way to know whether it's always true or whether it's always false, because there is no context here. That you don't really know what tomorrow refers to, meaning that you don't know what today is, what day today is, so therefore you don't know what day tomorrow is. So therefore this statement can sometimes be true, sometimes be false. Therefore there is no way to know whether this statement is always true or always false. Okay, so this is an example of an ambiguous statement, and that basically happens again when not enough context has been given to you to make sense of what the statement is all about. And the second situation here that can lead to ambiguity is when a statement is subjective, meaning that it's true for some people, not true for some other people. For example, let's say that some statement like dogs are intelligent. Okay, so let's say that dogs are intelligent. So this statement is this basically, call it statement or sentence, whatever you want to call it. This statement is basically a subjective statement, meaning that it depends on me whether I want to call dogs intelligent or not. Maybe I call dogs intelligent, but for example, my neighbor doesn't believe that dogs are intelligent. So then for him, dogs are, I don't know, probably stupid. But I might say that dogs are intelligent. So then there is no way to know, because there is no way to know. I mean, it's not something that everybody believes to be so. Some people believe dogs are intelligent, some people don't believe dogs are intelligent. So there is confusion there, there is ambiguity there. So this is also an example of an ambiguous statement. Now about statements being always true or always false, basically what you can say about that is that let's see if I need a new sheet over here. So about statements being always true or always false, let's have a couple of examples over here. For example, let's have this statement. For example, there are 8 days. There are 8 days in a week. Okay, so this is the statement that you have, and you want to know whether it's always true or always false or an ambiguous statement. So you know that you know it for a fact that there are actually 7 days for a week. I mean that's actually the definition of a week. So when you say that there are 8 days in a week, this statement is always false. Okay, if you say, for example, it is raining here, it is raining here. Okay, so what this statement is that it's an ambiguous statement, because there is no way to know what or what kind of place here refers to. Here is an adverb, and of course it refers to some place, but there is no way to know where here is. So then this is an ambiguous statement. Okay. The next thing that we have is the sun sets in the west. So the sun sets in the west. So we know it for a fact that, I don't know, based on astronomy and physics and things like that, but based on all of those things, we know it for a fact that the sun basically rises in the east and sets in the west. So based on that, this statement is always true. Is always true. Okay. Or let's say that, for example, Susan is a kind girl. Susan is a kind girl. Okay. So what this statement is that basically there is ambiguity there. I mean, this is an ambiguous or some sort of subjective. This is some sort of subjective statement, meaning that Susan can be kind to some, could be kind to some people, could be unkind to some other people. So this is a subjective statement. So this is for example, an ambiguous statement. Okay. Or we have another example here. The product of two odd integers is even. The product of two odd integers is even. Okay. Now the way that you can usually know whether these statements are true or false, you can check them for a few cases, and then you will know what's going on with the statement. But now I'm going to tell you more about that in just a few moments. But what this statement is saying is that the product of two odd integers, so for example 1 and 3, so for example 3 and 5, 5 and 7, 7 and 9, 9 and 11, 11 and 13, and so on and so forth. So the product of these two is equal to 3, the product of these two is equal to 15, the product of these two is 35, the product of these two is 63, the product of these two is 99, and 11 times 13 is equal to 13 times 11 is equal to 13. 13, that's 143. So you see that all of these numbers are actually odd numbers. 3, 15, 35, 63, 99, 143. So now I don't really know if I have talked about the concept of counterexample, but if you have some sort of statement like this saying that the product of two odd integers is even, and even if you can find two odd integers and the product of them is not even, that is enough to prove that this statement is actually not true. Okay, but we will talk about that more, what that means. So basically, but based on what you can see here, which is of course not enough, if you want to actually say that, for example, this statement is always false, and as you can see, it seems to be always false, meaning that whatever sort of basically odd integers that you multiply together, you're getting basically odd integers. Okay, so it seems to be always false, but again, you have to prove what you're saying, meaning that you have to prove this logically, which we will get to shortly. Okay, and that's basically that. And now again, there is some material here about and again, people are usually not very not very careful about the statements that they make, and I mean, what I mean by being careful about your statements, you are usually careful about the statements that you make if you are, for example, under oath in a court of law, for example. If you are in a court of law under oath, well, you could be basically careful about the statements that you make. Otherwise, people just don't care about the statements that they make, whether it's true or false, and so on and so forth. So, for example, if you live in an area and somebody asks you about the weather in that area, if it's, for example, if in a typical month it rains, for example, like if it rains for at most, I don't know, 15-20 days, then if somebody asks about the weather in that area, you would tell them that it rained, that in this area it rains every day, that every day it's raining. And of course, well, logically that sort of statement is not right, but Usually people kind of understand each other, but well, the statements that we make in our day-to-day lives are not, technically they're not, I mean, probably 85% of them are technically not true. And of course, you're not supposed to ask people for any sort of proof or anything, and you're not supposed to argue with people. Otherwise, you might actually have problems with people, or you might actually, people will actually call you weird or a freak or something like that. And after a short while, you will lose all of your connections with people. So that's basically, it's basically not very practical to do it in your day-to-day lives. You have to be very careful in a completely different ways, but not careful about the statements that you make. Or for example, people make such statements as, for example, it's very hot today. And it's very hot today actually doesn't mean anything, because if you want to talk about the weather temperature, you should actually provide somebody with the temperature. For example, you would say, for example, it's 37 degrees Celsius, for example, or 45 degrees Celsius, or I don't know, 90 degrees Fahrenheit or something like that today. But when you say it's very hot today, it doesn't mean anything, because even the same kind of weather could be cold for someone, could be hot for someone else. There is, I mean, for different people, the same weather even could be felt differently. So, but that's basically how we humans are, basically. Now, in a mathematical statement cannot be ambiguous. I mean, in mathematics, a statement is only acceptable or valid if it's either true or false. Okay, so this is something important that we need to add here. So a statement in mathematics, a statement cannot be ambiguous. Okay, meaning that if I write, for example, if I say, for example, A times B is equal to C, and then therefore what that means that B is equal to C to A, for example, right? So for example, something like this, A times B is equal to C and B is equal to C to A. Actually, in what I need to do is that I need to specify whether for example, what sort of numbers what sort of basically sets of numbers these three numbers actually belong to. Meaning that, for example, I should say that A, for example, belongs to the set of real numbers, or for example, B belongs to the set of natural numbers, and so on and so forth. I cannot just take three, for example, variables and just like that write A, B is equal to C, and then B is equal to so on and so forth. When you write something, there shouldn't be any sort of ambiguity about what you're saying. Okay? And so in mathematics, this is important. In mathematics, a statement is only acceptable or valid. A statement is acceptable or valid only if it is either true or false. Only if it is either true or false. Okay, so it cannot be an ambiguous statement. A statement is acceptable or valid only if it is either true or false. Okay, so for example, a statement, so for example, if you write 5 plus 2 is equal to 7, this is always true. This is a statement, this is always true. Always true. So 5 plus 2, so then you can say that 5 plus 2 is equal to 7. You call this a true statement. A true statement. Okay. And 5 plus 3 is equal to 7, for example. 5 plus 3 is equal to 7. That is always false. That is always false. And so you basically call this a false statement. Okay, so this is important. And so now we have a couple of examples here. So let me go through these examples and see if they are basically, if we can talk about a few of them at least, and then we will get to the next thing that we have, which is basically deductive reasoning. Okay, so the next thing that we have here is, I wanted to basically include some examples here, but it's not really necessary because we are going to be using this over and over again for different types of examples. So it's not really important whether we have examples here or not. But basically now the next thing that we have here is called basically deductive reasoning. Deductive reasoning. Okay, and deductive reasoning is basically, that's the main logical tool used in establishing the truth of an unambiguous statement. That is the main logical tool used in establishing the truth of an unambiguous statement. Okay, so if a statement is basically, if a statement is ambiguous, of course there is no point in establishing the truth. It's basically ambiguous. There is no truth about it. You already know that it's ambiguous. If it is not ambiguous, or if it is unambiguous, then in order to establish the truth of that statement, you use the deductive reasoning as a tool, basically. Now, in order to add, of course, this is not a very good example to understand deductive reasoning, because deductive reasoning is a simple thing, and we are going to get that in the second part of this. Basically, probably in the second video, we are going to be seeing a better example about deductive reasoning. But for now, I'm just going to give you something like a puzzle. So suppose that you are basically given 4 cards like this. So you have one card over here, another card over here, you have another card over here, and another card there, and you have basically A, V, 6 and 5 on these cards. Okay, and suppose that you're told that these cards follow the following rule. You are told that these cards follow this rule. If a card has an even number on one side, if a card has an even number on one side, then it has a vowel on the other side. Then it has a vowel on the other side. Okay, so now what is the smallest number of cards you need to turn over to check if the rule is true? The smallest number of cards you need to turn over to check whether the rule is true, meaning that you have the same rule that has been stated over here among these cards. Okay, but remember that you are looking for the smallest number of cards that you need to turn over, the smallest number. So of course you could turn over all the 4 cards in order to check basically the rule that you have been given, but since you're looking for the smallest number of cards that you need to turn over, you basically look at each card, and then you based on what you see, you have to decide whether you have to turn it over or not. If you don't have to turn it over, of course you don't turn it over, and you move to the next card. Okay, so that's basically like a game, but usually when most people would make a mistake over here, at least one mistake anybody might actually make, or will actually make. So now you need to read the rule over here, and the rule says that if a card has an even number on one side, if it has an even number on one side, then it has a vowel on the other side. So then basically, based on this rule, do you have to turn over this card over here that tells A over here? So basically, you know that the vowels are A, O, E, U. O, A, O, E, U, A, O, E, U. I think that's the only vowels that we have in the English language. Okay, so if you have an even number on one side, then it has a vowel on the other side. So that means that that means that if I now on the other side of this card, basically I have a vowel actually. So, and I have a vowel over here, and what that means is that on the other side of this card, if I have an even number, over here, so it says that if the card has an even number on one side, then it has a vowel on the other side. So on the other side of this card, if there is an even number, then of course this rule holds, meaning that you have an even number on one side of the card and a vowel on the other side of the card. And then if there is an odd number on the other side of this card, okay, if there is an odd number on the other side of this card, then of course there could be a vowel on the other side of the card, but the only rule that I have been given, basically the only rule that I have been given and the only rule that I'm checking is basically if a card has an even number on one side, then it has a vowel on the other side. But it doesn't necessarily say that, for example, it doesn't say that the card with a vowel on one side must have an even number on the other side, or what I mean by that is that basically if you have an odd number on the other side, still this rule is not broken, meaning that you have an odd number on one side and vowel on the other side, which is not a problem, and it doesn't break this rule. And if I have an even number on the other side, still the rule holds, so I don't have to turn this card over. Now about this card, so basically if I have to, so I don't have to turn this card over. About this card, if I have an even number on one side, and then if I have an even number on the other side of this card, then this side of the card holds a consonant, not a vowel. So then in that case the rule would be broken, right? So in that case I have to turn it over. And of course about the number being odd, of course I have not been said anything, so I don't have to worry about that. But if there is basically an even number on the other side of this card, and then there is a consonant here, then this rule would be broken, so I have to check for that. Now over here, this is an even number over here. So if on the other side of this card I have a vowel, the rule has not been broken. So on this side of the card I have an even number. On the other side, if I have a vowel, the rule has not been broken. Otherwise, if I have a consonant on the other side of this card, the rule has been broken. So I have to move this over to see what's going on the other side of this card. And well, on this side of this card I have an odd number. So if on the other side of this card, basically for example, I have a vowel, still this rule, it has nothing to do with this rule, so the rule is not broken. Now I got confused myself. So on the other side of this card, if I have a vowel, this rule has not been broken because this is an odd number, and here we're talking about even numbers. If on the other side of this card I have a consonant, still this rule is intact, it's not broken, so we don't have to move this card over. So the only two cards that the smallest number of cards that you need to turn over is actually two cards over here. So, and that would be 6 and V, okay? So the reasoning that I used here in order to arrive at this conclusion is basically called deductive reasoning, but most probably you did not actually understand deductive reasoning here, okay? So but in and of itself, this puzzle shows you basically a little bit about deductive reasoning, and of course, as I said in the second part of this, in the next video, we are going to get a better understanding, have a better understanding of deductive reasoning. Okay, and it's called basically deductive reasoning or deductive because we arrive, or basically we deduce or infer a result or a statement from a previously established statement using logic, meaning you establish something and then you use that as a basis of reasoning and then deduce something and conclude something, and then you come to the next conclusion, and so on and so forth until you get to basically where you want to get, wherever, meaning that you basically you kind of follow some sort of train of thought logically in order to get to some conclusion. That's basically called deductive reasoning. And so, for example, for this puzzle, if you paid attention to basically how I arrived at the final conclusion, was that I used a series of logical arguments, and then I deduced that I needed to turn over only these two cards, V and 6 over here, and also there is one more interesting thing that we do with deductive reasoning, and then using deductive reasoning, basically deductive reasoning helps us to conclude that a particular statement is true if it's a special case of a more general statement that we have that is known to be true. For example, if you didn't understand what I said, I repeat that. Basically, using deductive reasoning, you can conclude that a particular statement is true if it's a special case of a more general statement that is known to be true. For example, if you prove that, for example, the product of two odd numbers is always odd, meaning that an odd number times an odd number is always going to give you an odd number. If you prove that, if you prove this one, this is a general case. This is a general case. Okay. So now, based on this general case, you can conclude that, for example, I don't know, any sort of odd number. For example, this number over here times, for example, 134, for example, 563 is going to be that the product of these two numbers is going to be an odd number, because this is an odd number and this is an odd number, and over here we have established or proved that basically the product of two odd numbers is going to be an odd number. So then, since this is a special case of this more general case, then based on this I can conclude that basically without multiplication I can conclude that the product of these two numbers is actually an odd number, and without basically, and that would be also a case of deductive reasoning. Deductive reasoning is actually a very, very useful tool, and of course it wouldn't be possible to actually, I mean, if you were to talk about all the different ways that we are using deductive reasoning in our lives, and which in most cases are actually wrong, meaning that the way that we use it in our lives is most of the time wrong, but we use it in mathematics in many different ways, and it would actually not be possible to to talk about that. I mean, for that you would need days to talk about many different types of cases where you use deductive reasoning in mathematics in order to arrive at different types of conclusions. It's actually very it's actually very useful tool, and if it's so useful and it's so versatile that there is actually no way to talk about it, and there is no way to actually capture it. I mean, there is no way. There is, for example, about, I don't know, for example, you can very simply talk about a statement, and you can define a statement. You can say what a statement is. That there is no problem with that. Or, for example, you can very easily, for example, say what an odd number is, what an even number is. You can very simply, I mean, concepts like these, you can very simply talk about them in a few moments. Or if you're slow like me, it would take you an hour or so, but you can somehow talk about it, and you can put a few, I mean, you can limit it and put a few words around it and then talk about it. That's not a problem. But deductive reasoning is basically kind of, not even kind of, that's actually why, I mean, there was one of these mathematicians, I don't know who that was, Gauss or so, I don't know. One of these mathematicians actually asked a very interesting question, that why does mathematics actually work? Why does it work? It's actually a very interesting question. And nobody seems to know the answer to this question, okay? Even the mathematician that asked the question, he actually didn't know why mathematics work. Nobody actually knows why mathematics works, and it's like the biggest mystery in the whole, I don't know, in the whole world probably. Now, mathematics works because the very structure of mathematics is deductive reasoning. But now I'm simply saying that mathematics works because the very structure of mathematics is deductive reasoning. But if you want me to talk about deductive reasoning, I could talk about it for, I don't know, for years, and I wouldn't be over. There would be still some other aspect to it. It's so, I mean, it's a very beautiful thing. But the problem is that there is no way to define it. It's just, it goes in many different directions. It has many different, I mean, connections and associations with different things in mathematics. It's all interconnected. So it's just, I mean, it's just the most beautiful thing I've ever seen in the world of mind. But, well, when something gets so complicated and so complex, then there is no way to talk about it. We could say that, for example, we use deductive reasoning here and there, but then it's not the definition, and of course it's not possible to define it. Okay, so that is that. And if you want to, for example, if you want to actually know more about, if you want to have a sense of basically what deductive reasoning is, let me give you this example. This is actually a very good example. Okay, so for example, suppose the statement, for example, flower A flower A blooms only if the maximum temperature is above 28 degrees Celsius, on the previous day. Okay, so this is the statement that you have. Flower A blooms only if the maximum temperature is above 28 degrees Celsius on the previous day. That's the statement that you have. And you have another statement. Flower A in for example Valley B, okay, in Valley B, on for example flower A. So flower A bloomed in Valley B, on, for example, on September 25th, 2014, for example. You have this statement as well. So if you have flower A blooms only if the maximum temperature is above 28 degrees Celsius on the previous day, and then flower A bloomed in Valley B on September 25th, 2014. So now based on this these two statements that you have, you can conclude that the maximum temperature in Valley B on September 24th, not 25th, but 24th, 2014, was above 28 degrees Celsius. So here we say that flower A blooms only if the maximum temperature on the previous day is above 28 degrees Celsius. And then flower A bloomed in Valley B on September 25th, 2014. So what this means is that, what you can conclude from this situation, or from these two basically statements, is that the maximum temperature in Valley B on September 24th, meaning 2014, meaning the previous day, basically the day before this day, meaning one day before September 25th, 2014, which is September 24th, 2014, the maximum temperature was above 28 degrees Celsius. Now, the kind of logical thinking and analysis that we used in order to come to arrive at this conclusion is called deductive reasoning. Okay, that's basically that. So, and that's basically something I actually that's basically something that I'm actually in love with. That is, this thing, which I cannot basically define it in any way. This is something that I'm actually in love with. I actually love this thing, whatever that is. You know what I'm talking about, hopefully. Okay, so that is that. So in the next video we will talk a little bit about theorems and conjecture and axioms and things like that. So I think we will have a couple more videos to basically to have a basically to come to the end of this discussion, and then we will go back to our discussion of real numbers and things like that. So I'll see you in the next video. Thank you.